So, one of the things that I had suggested to you or told you was possible was that you could just assume a flow of current. And so if I were to make an assumption that, say, current 1 is going this way, then only a couple of things are possibly true. I could have current 2 and current 3 coming into the node. I could also have current 3 going out of the node, or current 2, but you only have a couple of options if one is that way. And so if I just make up those current values, and it really wouldn't matter what you labeled current, it helps if you have I1, I2, I3, and sometimes you get to match the 1, 2, 3s with the resistor numbers, sometimes you don't, and that's no big deal. Other thing to note is that if that's the case, then down here it must be true, if I'm right, that current 2 and 3 are also coming back up around the other side. All right? So we would be able to write an equation, I1 equals I2 plus I3. So that would be our node rule, and we could make it either one of the nodes in this case because the circuit is simple enough. So Kirchhoff's node rule would give us that equation. Yay! We only get one equation out of this circuit. If they had other larger circuits, we could have multiple current equations. Probably not enough to solve the system. Certainly not. We need at least 2 more equations since I have 3 unknown variables in this, or at least 3 unknown so far. So that would give us that. So now what we can do is write some loop equations, all right? And we can start with the battery. And remember, the battery's plus side is the big one, minus side is the small one, and we can choose any loop direction we want. You know, if I want to traverse the loop in this direction, all right? So according to those rules that I showed last week, if I go uphill through a battery, if I go from minus to plus, which is what I'm doing with this direction, then that means that's a write our loop rule since we're doing that. That's a 12-volt voltage source. It's going to be positive because I'm going uphill through it. And then I'm going to go around my loop. I'm going to go through that node and through resistor 1. All right, so, this loop. And when I go through resistor 1, that's going to be, since I'm going in the direction of current flow, the assumed current flow, whether it is or isn't, we'll find out, then that's a negative drop. And so I can say minus, and I'm going to write I1 R1 because that's voltage 1. Ohm's law says that this is, V equals IR. All right? So I'm putting that in there. Now I'm going to erase, this resistor value. In fact, I'm going to come back in. I'm going to write 4I1 because the resistor value is 4 and the current value is 1. Now this is the way you see it in all the textbooks and online examples. There's always some number in front of the current label, and that number is the resistor value. It's resistance times current, or current times resistance, doesn't matter what order. So since the 12 was a voltage, I can only add or subtract other voltages. Apples to apples, oranges to oranges. So I have a minus 4 I1 going through that resistor. Then I'll come through here, and this is going to be a 3 ohm resistor, and I'm going again in the assumed direction of current flow, so that's negative 3I2. All right, and then back up to battery, and that means to 0. So that's one of the loop rules. The other loop rule, I can come out of this 5-volt battery, and I'm choosing to keep the voltage source a positive by going uphill through the battery. And so another rule, 5, so that's a positive 5 volts. And so we'll go uphill through that battery to the node, and we're back at that same resistor, minus 4I1. And then we'll come back to the node, and here we are going through this next resistor. This is only a 2 ohm resistor, and it's I3. Since the way we had decided to label that current 3, we go back to battery. That means that equals 0. So we have our 2 loop rules. And we know that we only have 2 loops because you can see the 2 loops. I could have written a loop that goes all the way around, and that means one of the batteries would be plus and the other would be minus. I'll do that just for grins. So what would happen if we did this loop? Just for giggles. So that would be 12. And then we'd go downhill through that battery, and then we'd go uphill, so to speak, backwards through that resistor. That means that would be a plus 2I3. And then if we were continue, now we're going downhill through that resistor, so to speak, minus 3I2. And then we'd go back to source, and that would be 0. That would be an equation that we could write, and we'd have 3 equations and 3 unknowns. We could get the voltages, but or the currents out of that. That's a valid way to go. I'm not going to solve that one, but it's a valid way to go at the problem. And so let's simplify things here. So that first equation, this loop here, if I just change the signs on the variable terms to be positive, then I have the sum of those two things equals 12, and then in the next one, the sum of those two things equals 5. So a 4I1 plus a 3I2 equals 12, and then another 4I1 plus 2I3 equals 5. And then we would have the original node rule equation that would give us our third equation for that third unknown. So what we have here, that current equation and these 2 current equations allow us to solve the system of equations. And so I had told you, why bother doing it by hand? Just take the easy path and solve it using one of the online calculators. So if we come to a place like Mathway, the ultimate math cheating app, because you can take pictures of things with your phone and it'll solve it for you. I can actually type in the equations, and so let's do this. Let's see, have to use the screen to type. I'll have to use X, Y, and Z on this app. When I was at a regular computer, you can actually use the keyboard to type in different letters and whatnot, but this one going to be difficult. So I1, I'll call that X, plus I3, I2, which I'll call Y, will equal 12. And I can put a comma there. And then I had a 4I1 plus a 2I3, so I'll have a 4X plus 2Z. I'll use Z for the I3, equals 5. And then I had the original loop equation where I1, which I'll call X, equals I2 plus I3, or Y plus Z. And if I hit the little go button, it just pops out the answers of 3/2, 2, and minus 1/2, which if you ran the simulation, you would know that those are the currents that actually come out in the FET thing. So here's the rub. I told you that if you ever get a negative out of your solution, remember we assumed a direction of current flow. And either that assumption is correct or it's not. Assuming that all the math was done correctly, that I wrote the loop equations correctly, and that they were solved correctly. If you write them correctly, the solvers are going to get them right for you. Pretty low chance that the solvers are wrong. They kind of worked that out already. Then that means if you get a sign change, meaning, or any negative, means that you were wrong about the direction of that current. And so you would go back and change the direction. So apparently, I3 is going the other direction. All right? So let us come back here, and we would have to change the direction of I3 to be this direction. So it's splitting off and going, instead of them coming together at that junction, they're splitting at that junction. And that means this I3 has to change. Otherwise, they're correct. We were correct about the battery over here, the 12-volt battery, going in the direction that it's going, and you would expect that. Why would we expect the 12-volt battery to be the winning pusher in this case? It's greater than 5. So why would the 5-volt battery, which is, they're both pushing up, so to speak, if you want to think gravitationally, why would you expect the 5-volt battery to be able to match, much less exceed, the 12-volt battery? Okay, so we're going to be pushing current backwards through the 12-volt battery. All right, so basically we probably just lowered the voltage of the circuit in that regard. Okay? So that's how this works. And every individual step is easy, and if you mess up one of but that's the nature of systems of equations. The math is technically easy, but if you set it up wrong, then you just have an ongoing mess that you don't know why it's an ongoing mess, and especially if you happen to do it by hand. That just multiplies errors too. So I don't recommend the by hand method, except for there's times where sometimes it doesn't pay to. You'll see here in the next, I think the next two circuits have that going for it in one or more places, where it's like I could just solve for this thing right now. Okay, so move forward. All right, so here's this circuit, and again, we can make some assumptions about current flow. So I'll do the same thing as before. I'm going to say that current is coming into this junction. All right. I'll call this I2 since it's going through resistor 2, and I'll call this I3 since it's going through resistor 3, and since this other one's about to go through resistor 4, I'll call it I4. It really wouldn't matter what I called them, but that's what I called them. Up on the top there, we could do anything. I'll just say I1's going this way. You might suspect that that's wrong because the battery on the right is a 10-volt battery. The battery on the left is a 5-volt battery. There is, however, the resistance at that first node here, this resistance is smaller than the resistance, or they're the same, I'm sorry. Pay attention here. So those two nodes are facing equal resistance at each battery, so I actually would expect I1 to turn on this. Okay, it's gonna rat us out. We'll see. We'll do the math, but you can use those are perfectly valid things. So you know what? I bet you it's going the other way. I'm gonna go ahead and leave it like this. Okay, and we'll see how that works out. So let's take a look here. So what I want to do though first is note that if I take this loop right here, notice that I have two known voltages and one unknown current. That's going for the throat. That's the easy kill. So let's do that, and I'll go in the direction that I indicated with that arrow. Okay, so we have plus minus, plus minus. So this means that I'm going to have a 5-volt uphill, meaning positive, starting at that battery on the left over here. I'm going to go up through resistor 1, and since I'm going with the flow or assumed flow of current, that's going to be just 1 ohm times I1. So I'll just write I1 since we don't write coefficients of 1. And then I'm going to go down through this other battery, but since I'm going downhill through that battery, that's going to be a minus 10. And then I go back to the other battery. So it means I just solved directly for I1. And I1 equals a negative 5 amps. Well, right off the bat, we just verified the hunch that current's actually going the other way. Maybe the other ones are right. We'll find out here in a second when we go to solve all this. Okay. So, I guess we need to be more careful here though, because there's more currents. So up here, you know, I had that node, and I guess we could write a node equation. We probably should for that one. So node rule, so if this is correct, then I'm going to have I4 equals I2 plus I3. And let's see, this node here should be, well, let's, got these other nodes here, so it looks to me like when I4 comes down to the bottom here, it's going to do a couple things. It has to go this way. I'm going to call that I2 since it comes back up to this other area. And I'm going to call this I5, new current. Okay? And so I5 is coming into this node here. And so what does that mean? If I1 and I5 are coming into that node and funneling off as I3, And that means I have I3 equals I1 plus I5. But I just found I1, so this means I could write I5 will equal I3 plus 5. And so this equation and that equation are going to become useful equations because I have a common unknowns of 2 equations with 3 unknowns in there. All right. So we got a couple of node rules. We could probably write one more for the other node, but we'll see if we need that when we get there. All right. Let's take a trip around this block right here. All right. So, loop rules. So that's going to be uphill through that battery, positive 5, minus a 2I2, this battery right, or resistor right here, and then a minus a 4I4 for that one right there. Get rid of my circle. Oops. And then going back to battery will be 0. So that one I can write that equation as if I just change the signs on the variable terms, this will become a 2I2 plus 4I4 equals 5. Then this other battery, I can go the other direction so that I get positive 10 volts out of that battery. I'll go 2I3 through that top resistor R3 since I'm going in the same direction as assumed current flow. That 4I4 will pop back in and then we'll come back to 0. And then this equation will, again, same little trick, equals 10. So now I have this equation and this equation. So let's see here. I have I2, I3, I4, and I5. That's 4 unknown variables in these 4 equations, which means this is a system of equations, and if it's a correct system, it will be solvable in the toy. All right. So I'm going to let's see here. Let's bring that. Mathway thing up again. So let's see if I can keep all of this straight here. See, we had a 2 I2, and I2 will be Y, plus 4 I4, so we'll call that'll be, oh, we don't have an extra letter. That really stinks. Here we go. We'll call that S. And that was equal to 5. Then we had 2I3, which will be, I3 will be Z, plus that 4I4 again, so 4S, since S is standing in for our I4. That's our second equation. Then we had I4 equals the sum of I2 and I3. So that means S equals, what was it, I2 plus I3, so Y plus Z. And yes.
You didn't set that second equation equal to anything.
Yes. That needs to be equal to 10, I believe, yes. There we go, thank you. And then the last one, I5 equals I3 plus 5, so our T, we'll make that T, equals, what is it? A Z plus 5. So let's see if this was entered correctly. Here we go. So we get one of our currents has to reverse. I3 needs to go the other direction. We already did I1 and figured out that had to turn around. So we have those four currents. We could go back and label them, and if you run the PhET simulation, you'll find that this is exactly what it does. And this should match the conventional, so if you switch it from electron to the conventional flow with the red arrows instead of the blue dots, you'll see those same directions going. So Kirchhoff's laws give you, should give you conventional current flow directions, is the idea here. All right? So that's good to go here, so let us get rid of that and move on to the last one. So this one is actually pretty easy to do. So right off the bat, I'll stick with my be consistent here. Keep making that junction work that way just for consistency's sake. All right, so this loop here. Nice thing about this loop here, it has one voltage source and one voltage drop, which means I should be able to very quickly obtain the current value for that one. I'll go ahead and write my node rule though. I3 equals I1 plus I2. Now let's get to this loop rule. So 50 volts, or 50 minus 100 I3. That's what's going through resistor 1, and that goes back to the battery. So this means that current 3 is just going to be 50 over 100, or 0.5 amps. So right off the bat, we get current 3. Now we can take this other loop, come out of this battery, and go through all these other ones, and so one of the currents is known. So we'll have 25 volts when we pop out of the top of that battery, minus 100 I2, because that's what's going through resistor 2, minus 100 I3, which that'll just turn out to be a 50, minus 100 I2 equals 0. Now, this has to be I2 because it's coming back up this way. right? And this would have to be I1 since it's going back up through the battery to where I1 is, right? So this equation here, notice that you have a minus 200 I2 there. And so we'll have 25 minus 200 I2 minus 50 equals 0, because this right here is just a minus 50, because we already know that this 1/2 amp will go into that value for I3. All right? So this means that I have, let's see, 200 I2 will equal negative 25, and so I2 is going to be minus 1/8, or negative 0.125 amps, which, by the way, would be the same as 125 milliamps. All right? So we have, in this thing, we know that I3 is 1/2 amp. I2 is a negative 1/8 amp. And if this equation up here at the top is correct, then that means I1 will just be I3 minus I2, and that should give us a 0.625. So we didn't need to bother with, we'd spend more time typing it into the solver than just doing it. But you can certainly use the solver if you want. Okay? So that's the application of Kirchhoff's node and loop rules from easy to not as easy in there. So I've given basically an easy, an intermediate, and a hard in this homework / lecture thing. So you got a chance to take a swing at it over the weekend, wrapping it up today. And so what we'll do is we'll have a kind of a group test on Wednesday with a similar set, and that'll be part of what the puzzle is on Wednesday. And we'll wrap up circuits on Wednesday with the celebration of knowledge experience. That will be largely just the circuits, and there'll be a take-home part for other things that we've done.